Okay, hello everyone. So today I'm going to discuss some horizontal motion problems and the process by which we can answer them. Let's start with a very simple one, which is very similar to the ones we were exposed to when we were just choosing which equation to use. Okay, so an airplane accelerates down a runway at 3.20 meters per second squared for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. Okay, so in order to make it organized, I again reiterated that we will use the GRESA approach. And G in GRESA stands for given. So what are we given in this problem? Well, we're given this value over here. Meters per second squared is an acceleration. Okay, so we'll write that down. We're given the acceleration. And 32.8 seconds. Now, seconds is a unit for time. Therefore, we are also given the time, 32.8 seconds. And we're being asked, R means required, we're being asked to determine the distance traveled by the aircraft before it takes off. So we're looking for delta x, displacement. Okay? Now it seems like there's something missing here, but actually you have to take note that when you are dealing with aircraft in particular, you start off with 0 because your airplane starts from rest and then it accelerates down the runway and then it will build up speed. So one assumption for airplane problems is that VI is 0. Okay? So we're given delta x, we're given VI, we're given time, we're given A. Which equation do we now use? Well, the equation that has all of these, if you look at your equations, would be the rectangle plus triangle, so that's delta x, VIT, 1/2 AD squared. Okay, let's check. Do we have a delta x? Well, we're looking for it. Do we have a VI? Yes, we do, and it's 0. Therefore, this entire thing would cancel out because 0 times anything is simply 0. Okay, 1/2 A, do we have an A? Well, we do, so that's a check. And we definitely have a time. This is a check. We can therefore start solving using this equation here. Okay, let's now move on and solve. Delta x is equal to VIT plus 1/2 AT squared. We know that VIT has already been cancelled out, so this equation simplifies therefore to 1/2 AT squared. Simple as that. Okay, we're looking for delta x, 1/2. What is A? A is 3.20 meters per second squared. Okay. What is your time? Your time is simply 32.8 seconds. And don't forget that entire thing is squared. So now we have something which we can plug into our calculator. Let's try it out. So the seconds will cancel out. You'll be left with a unit of meters, which is consistent to delta x. Okay, so let's get my calculator real quick. So that's 1/2 times 3.20 times 32.8 squared. That will give me 1721.344. The unit now, because the seconds canceled out, was meters. Okay, now let's check significant figures. Okay, the 0 doesn't count because it's 0. We're only going to take note of this one, which has 3 sig figs, and this one, which has 3 significant figures. And therefore, when we plug all that in, we're simply going to get, what's this? 1720 meters. Final answer. That's your A. Okay? So as long as you're organized with your problem solving, as you could see, we should be able to be fine with horizontal motion problems because it's just a matter of choosing an equation, plugging it in, then solving, and then checking for sig figs. Okay? Now let's up the difficulty a little bit. Now let's see what will happen if you're trying to prove something using horizontal motion. So let's read the problem. During World War II, an American Hellcat fighter plane is running low on fuel. With the aircraft carrier USS Enterprise 245 kilometers away, The Hellcat pilot decides to cruise towards the Enterprise at a steady speed of 83 meters per second. If the plane only has enough fuel to keep flying for another 52 minutes, will the plane make it to the carrier to land safely? Justify your answer with a mathematical solution. Okay, so it's a long problem, but one thing that you should do is always to take note what are you given first. Okay, so we know that the aircraft carrier is 245 kilometers away. This is a sign that we are given a delta x of 245 kilometers. Okay, now for consistency, let's convert this into meters, which is the SI unit. So this is simply times 1,000 for 5,000 meters. Okay, we're given that. Let's see, what else are we given here? We're given 83 meters per second. And is this a VI or a VF? Well, it says here that the plane is cruising at a steady speed. Therefore, it is both the VI and the VF. Your speed does not change, and therefore, initial velocity is equal to the final velocity, which is equal to 83 meters per second. Okay? Now, what else are we given here? Well, we know that it's a steady speed, and therefore that means that the acceleration is also 0. Okay? And finally, we are given a time element because we know that the plane can only fly for 52 minutes. And one thing we can do to this 52 minutes would be to convert it into seconds, just to make it consistent with the SI. So we have 52 minutes, 1 minute, 60 seconds, minutes cancel out. We'll get 52 times 60 gives us 3,120 seconds. Okay? So now this is all we're given. What are we being asked to look for? Well, it's not actually a displacement, a time, or a velocity. We're being asked to answer a simple question. Will the plane make it? So, will the plane make it? Now let's plan. How are we going to prove that the plane actually made it to the aircraft carrier and landed safely? Well, one thing we can do would be to prove that your delta x exceeds 245 kilometers or 245,000 meters. How will this prove it? This means that you have enough fuel to reach 245,000 meters. Okay, so anything in excess of that means your plane will definitely make it. One thing we can also do would be to check the time, okay, and make sure that the time is less than 52 minutes or 3,120 seconds. Okay, because if your time is less than 52 minutes, then your plane can still keep going. If it's greater than, your plane will not have enough fuel, your plane will crash. So you're going to have these options. We can use the delta x approach, we can use the time approach. So given that we're looking for delta x and we're trying to prove that it's greater than 245, what can we use? Well, actually we have two options here for equation. First, we can use delta x is equal to VIT plus 1/2 AT squared. Okay, because we're given delta x, we're given A, we're given VI, and we're given T. But we can also use the other area equation, which is VI plus VF over 2 multiplied by T. Why can we use this? Because we know VI, we know VF, we know time, we're looking for delta x, we can definitely use this, okay? So these are two approaches that we can do. Let's try to prove using both delta x and time and using these two equations. Again, you don't have to prove both of them. You just have to prove one. Once you get that delta x is greater than 245,000 or that t is less than 3,120, you're good. But for the purposes of this video, I want to show you that both approaches will work. Okay? So first, let's try proving using delta x. And for delta x, let's use the first equation that I put down. Delta x is equal to VIT plus 1/2 AT squared. Okay, we know that A is equal to 0, and therefore this will simply cancel out because anything multiplied to 0 is 0. Simply delta x is equal to VIT. Let's rearrange, or actually we're looking for delta x, so this should be fine. So that's VI, 83 meters per second, multiplied to time, 3,120 seconds. Okay, now let's solve. That's simply 83 times 3,120. That gives me 258,960 meters. Now let's compare. Is this greater than 245,000? Well, definitely. It exceeds 245,000. Therefore, we can then certainly say that the plane lands safely. That's your final answer. Okay? So this is one way to do it. Now let's check the other way. We can also do this through time. And let's use the other equation just so we have some variety in what we're doing. Again, this is not necessary to do both. I'm just showing you an alternative by which you can solve the problem. Okay? So one way to do it through time. Let's get the equation out. Delta x is equal to VI plus VF divided by 2 multiplied to the time. Okay? So this time we're trying to prove the time, so we don't know time. But we know delta x to be 245,000. We know VI and VF to be both 83. And we'll multiply that to 2. There's a 2 at the bottom. Okay? And we're trying to get the time. The 2's will just simply cancel out because they're both 83. So 245,000 is equal to 83 times t. One way we could do that would be 245,000 divided by 83 because this is simply going to go as the denominator. Okay, so 245,000 divided by 83 gives me 2951.8 t. So that's 2951.8 seconds. Now, is this less than the time that we set, which is 3,120? Definitely, 2,951 is less than 3,120 seconds. Therefore, it is also proven that your plane lands safely. Okay? So there are many ways to prove a problem. There are also many approaches, so don't be boxed in by just one equation. Okay? You can use multiple approaches to solve and get the same result. So this is proving. Now, let's challenge ourselves a bit more by going with bodies or problems that involve two moving bodies. Okay? This one now requires extreme visualization. But one way we could do the visualization bit would be to sketch the problem. Okay? Once we sketch, we should be able to visualize, okay, this is going this way, this is going that way, and therefore, we can make our solution. So let's try it. Phil, a striker, is taking a free kick against Neil, a goalkeeper. Phil placed the ball a distance of 30 meters from the goal and took aim for the corner of the goal. With the ball initially at rest, he kicked it to a final velocity of 25 meters per second. Neil took 0.50 seconds to react before he dove towards the ball at a constant speed of 2 meters per second. If Neil's initial position was 3 meters from the corner of the goal, did he make it in time to save Phil's shot? Justify your answer with a mathematical solution. So a classic proving problem. But this time, unlike the other one, we have two bodies moving in different directions. So let's do it first. So before we go to GRESA, one thing we could do to visualize is to simply sketch the problem. So let's put the striker here, Phil. Neil, the goalkeeper, goes there. Okay, Phil takes a shot going towards the corner of the goal. So let's see if we can draw a goal over here. Okay, goal. Let's pretend that this is the goal. Takes a shot towards the corner. You know that the shot started out at rest because it's a free kick, and it ended with a final velocity of 25 meters per second. You know that the shot was taken 30 meters from the goal. Now let's see. Neil took 0.50 seconds to react before he dove towards the ball at a constant speed. So we know that it's a constant speed, therefore VI is equal to VF, which is equal to 2 meters per second. This also tells us that the acceleration is 0 because it's a constant speed. Okay? And you know that Neil is also 3 meters from the corner of the goal because that's the width of the goal post. So now we have to determine if did he make it in time. Okay, so what are we given here? Well, in this kind of problem where there are two bodies, it is very useful to separate it by the two bodies involved. So we have Neil and Phil. Okay, so let's take a look. So for Neil, we know that we have the delta x of Neil. He has to travel the 3-meter width of the goal. We also know that he travels at a constant rate of 2 meters per second. Okay? And we know that we don't have the time. We're looking if what is Neil's time. Okay? But there's also another catch. It took him 0.50 seconds to react. So we know that Neil's time is going to be the time that we solve plus 0.50 seconds. Okay? Furthermore, let's go to Phil. So for Phil, we have a VI of 0. We have a VF of 25 meters per second. Okay? We know that the delta x is 30 meters. Okay? And we're now looking for the time of Phil. And this is what we're going to compare. We are required to see if Neil makes it to save the shot. So if the goalkeeper saves the shot, he should be able to make it to the corner of the goal before the ball does. Okay? So the time of Neil must be less than Phil in order to prove that it works. So now let's check. What equation can we use for this case? Well, in this equation, delta x, vi, and t, and we also know that acceleration is 0. For Neil, we can use the equation delta x is equal to vit plus 1/2 at squared. But with the knowledge that acceleration is 0, therefore, it's simply vit. For Phil, we can use, we have vi, we have vf, delta x, time of Phil. Okay? So let's take a look. We can use delta x, vi plus vf divided by 2 times the time. Okay? And we're going to compare the 2 times and make sure and check which one is faster. Okay? Now let's solve. Let me just allot some space for this. Okay? So let's first solve Neil because the equation looks a little bit simpler. So for Neil, delta x is equal to vit, and with a bit of rearranging, we can get that delta x over vi is equal to t. Okay? We know that Neil has to travel 3 meters, and we know that he will start at an initial velocity and maintain that initial velocity of 2.0 meters per second. Okay? And this is all going to be equal to time. So let's get my calculator. 3 divided by 2 is simply 1.5 seconds. So that gives us t is equal to 1.5 seconds. However, if we want to get Neil's time, remember he reacts late. Okay, goalkeepers don't have superhuman reflexes that allow them to just go and get there. They have to have human reaction time. So we have to add this time to 0.50 seconds, okay, to get Neil's actual time. So 1.5 plus 0.50 is simply 2.0 seconds. Remember, sig figs. So this is Neil's time. Now that we did Neil, let's try Phil. So for Phil, we have delta x is equal to vi plus vf over 2 multiplied to the time. Okay? So let's see, what is our delta x? Our delta x is 30 meters from the goal. Okay, our vi, what's vi? Vi would be 0. Our vf, 25, divided by 2, multiply it to the time. Now we can use algebra, but I'll teach you a different technique by which we can solve this by simply plugging in the equation. Okay, so we go 30. Alpha equals, that presents an equal sign in your calculator, So it's going to be 0 plus 25 on the top, as we have determined, divided by 2, times, let's set a variable. Let's say x. Okay, so that's the equation we're dealing with. So now, in order to solve for x, we just press shift and then solve. Okay, then we press the equal sign at the bottom, and there you go. X is simply 2.4. But here it's t, so we can solve that t of Phil, 2.4 seconds. Now let's check. The goalkeeper gets there in 2 seconds. The ball struck by Phil gets there in 2.4 seconds. So who is faster in this case? Well, it's obvious that the goalkeeper wins because it's much slower. Therefore, final answer, Neil saves the shot. Okay, so in summary, this is actually a pretty simple kind of mathematical application, because as long as you're organized with Gresa, and as long as you can visualize by doing sketches, by checking which equation you have to use, you should be fine, because it's just a simple plug it into your calculator and then prove and solve. So I hope this video was helpful. Thank you for watching, and I wish you luck in the remainder of our discussion for horizontal motion. Take care.